Andreas actually is a true Courant Institute member. He is a student, the only student and the best student of Helga Tverberg, and he sent Andreas to New York to learn from the masters, and here are the two masters. And now Andreas is the master. Please.
Thank you for the kind introduction. Yeah, you already said it, that I was lucky enough when I was a young PhD student to be sent to the masters in New York and learn from them. And this was a great time, and I really did learn a lot from them. And so today I want to just talk about some of the works, my favorite work of theirs maybe, and some of the influence and impact it has had on current research. Right, so this will mostly be remembering the work of Eli and Ricky. Okay, and the first thing I want to talk about is the classification of planar configurations and the work they did on order types. And this is really where their collaboration started. And well, Janos already mentioned this, but I thought it was nice to include this part, which is from the introduction of their very first paper. And it sort of summarizes their goals and dreams at the time. And it says, our primary concern is with problems related to convexity, such as the Erdős-Székely's conjecture. Suppose, for example, one wanted to ask a computer to test each non-degenerate plane configuration of 17 points to determine whether it contains a convex hexagon. How could the computer, even in principle, generate finitely many 17 tuples, such that any two are essentially distinct and any 17 tuple essentially the same as one of those generated? I think this really captures what they were trying to do in the beginning of their work. And they came up with this model, which many of you know, called the allowable sequence. And this is a permutation sequence. So each of these PIs is a permutation of the integers 1 to n. And we'll just assume that it starts with the permutation, the natural order 1 to n, and it ends in the reverse order, so decreasing order. And second condition is that when you go from one permutation to the next one in the sequence, this should differ by reversing one or more non-overlapping increasing substrings. And this is what the combinatorial model that Eli came up with and proposed to Ricky called the allowable sequence. So they wrote many papers about this, studying properties and so on. So here on the left, I have written down one specific allowable sequence, and you can see highlighted are the increasing substrings that are being reversed when you go to the next step, right? And where does this allowable sequence come from? Well, it comes from this point configuration. And you can see if I take a vertical line and I sweep from left to right through this configuration, I will meet the points in the labeled order 1, 2, 3, 4, 5, 6. And if I start rotating the line, you see that it's evident that you change the order as soon as you pass the direction of a line spanned by the point configuration. And so the first one you will pass is 3, 4, and that's this one. Next, you will pass 1 to 4, which is parallel to 5, 6, and that's these switches that are happening here. And another way of representing this permutation sequence is simply by recording the position in which the numbers appear. So, and that would be in what they call a wiring diagram here. And you see that this wiring diagram, well, since you start at the natural order and you end at the reverse order, each of these wires should cross each other, and you actually are looking at what you can think of as a pseudo-line arrangement. And that brings me to the first very basic theorem of theirs about these pseudo-line arrangements, which is every allowable sequence of permutations can be realized by an arrangement of pseudo-lines and also by a pseudo configuration of points. And moreover, an allowable sequence is realized by an actual arrangement of lines if and only if it's realized by an actual configuration of points. And this is just projective duality. But what they found was that these permutation sequences are actually more general than configurations of points. So there are permutation sequences that do not actually correspond to any real point configuration. And here is a simple permutation sequence, or a simple allowable sequence. Simple meaning that at each step, a single pair swap positions. And we can record this in something called a swap sequence. And here is the corresponding pseudo configuration. And you see, I cannot realize this by real points in the plane. I need to connect the points by a pseudoline arrangement. And that's why we call it a pseudo configuration. And so this was one of their first discoveries, was this configuration called the bad pentagon. And this is the smallest non-realizable allowable sequence. And so they introduced these allowable sequences. Their goal was to solve problems, combinatorial problems about point configurations, right? And it turns out, so they studied a lot of the properties and they promoted these allowable sequences, and there were a number of problems that were solved using this combinatorial model. Most notably, I think the slope problem solved by Peter Ungar. This is even it's such a beautiful proof. It was included in Eigner and Ziegler's proofs from the book. So this is a true classic. But there are many other problems that where allowable sequences were used. Alon and Urey counted the exact maximum number of at most k-sets, number of balanced lines. This was Pach and Pinkasi, and many other places are these allowable sequences used. Let me also mention that some other problems. So the halving set problem, we know the best possible bounds here, and Andrew's proof of the Erdős-Ekeresz problem, at least the asymptotic proof. These were not proved using the allowable sequences, like maybe Eli and Ricky's dream was, but we have later, you can go through and you can really check that they hold for allowable sequences as well, right? So these, and now why would we want to do that? Well, it turns out that, well, from what we see here, for example, allowable sequences are more general than point configurations. And so when you are, so we want to, it is an interesting problem to know what are the combinatorial properties of point configurations that actually hold in this more general combinatorial model than just the, what you get from real point configurations. And so that's why there is we would want to check that these proofs by Day and Suk and many of these other combinatorial problems on point configurations actually hold in the setting of allowable sequences. And when we are there, then you may also, the next natural question that arises is actually how much more general are these allowable sequences? How much more general are they than actual point configurations? And that's the next result of Eli and Ricky I want to talk about. And this is semi-algebraic sets and counting allowable sequences. And we have this one theorem by Eli and Ricky, which says that the number of distinct simple allowable sequences that are geometrically realizable by point configuration is this number here, roughly 2 to the n log n. There's some constant hidden here that maybe is not completely known, right? And when they discovered this, that was quite a surprise because they already knew that there were far more allowable sequences than this number here. And in fact, it follows by results of Stanley and Edelman-Green that the number of distinct simple allowable sequences on n elements actually is of the order 2 to the n squared log n. Far more than the amount you get that are realizable coming from a point configuration. And so this was at first quite some surprise to them. And it shows that this permutation model, the algebraic allowable sequences, is it's a far more general object. But more importantly, this theorem, I think, is the proof that they discovered. The proof of this theorem relies on something called Milner's theorem, which is a theorem that basically you can bound the number of connected components of a semi-algebraic set, and you bound the number of connected components in terms of the sum of the degrees of the polynomials that define it. And the relation to allowable sequences, well, in the allowable sequence, we want to know the order in which these directions appear. All right, so what is the order of the directions determined by the points of your configuration? And it turns out that, well, which of these directions appears first can be solved, or is determined, you can solve this by a simple polynomial inequality. And then you sum up all, or you take the product of all these polynomial equalities. This gives you a semi-algebraic set, and you plug it into the Milnor theorem, and this is basically how this bound appears. Okay, and this method, I think, has had a lot of applications later in discrete and computational geometry. This is a very fundamental bound, and they use the same method to bound the number of order types, which is a coarser classification of point configurations, coarser than allowable sequences, but similar. You can also bound the number of simplicial polytopes using the same Milnor bound. And more generally, and this was maybe explored more later, something called semi-algebraic graphs and hypergraphs. So these are graphs and hypergraphs that are determined by semi-algebraic relations. And the basic moral here is that as soon as there's some semi-algebraic relation that is defining the combinatorics here, then the number of configurations drops drastically, becomes much, much less. And this is even in these days, quite extensive theory of semi-algebraic graphs and hypergraphs has been developed, and we know a lot about the extremal properties of such configurations. And basically, it says that the combinatorial complexity decreases and becomes, in some sense, simpler once these are defined by these semi-algebraic properties. And I think Eli and Ricky's result is kind of a precursor to this theory that now exists. Okay, so I want to now mention another result. So this is last thing I want to mention about the order types or allowable sequences is some recent work in a different area, but it's sort of very interesting, and it's sort of bringing on the legacy of Eli and Ricky. So and it's very interesting results. So I need to change I'm going to change the terminology a little bit here. So they call this random sorting networks. Now a sorting network is just the same as what Eli and Ricky called a simple allowable sequence. Okay, but the way that they study this is consider the space of all possible sorting networks on n elements. So just all possible simple allowable sequences, and consider this as a probability space with a uniform probability. Now the result from the previous slide that I showed you is the following here. And it basically says that a random sorting network, the probability that a random sorting network is geometrically realizable by points is very small, tends very fast to zero, right? That is what Eli and Ricky discovered using the Milnor bound. And in recent years, people from probability theory have been studying these random sorting networks, and they could make a bunch of very interesting conjectures and results. And it's kind of in the spirit of what Eli and Ricky originally did. Now, remember, Eli and Ricky, originally, they wanted to generate all possible 17 tuples of points in terms of allowable sequences and check for the Erdos-Ekers conjecture. But they quickly realized there are too many. It's impossible to generate all of them. But it turns out that due to certain combinatorial bijections discovered by Stanley and Edelman-Green, you can sample in a very efficient way. You can sample a random sorting network or a random allowable sequence. This can be done. Large ones can be sampled in a very efficient way. And this way they could do experiments and discover a lot of things. And one of the most spectacular results that I'll mention here, it's kind of mind-boggling, is the following. So you take a random sorting network, a large one. So this is of size n. So n tends to infinity. It's large, but from this large one, you select again randomly m of the elements in the sorting network. Okay. And if you look at the permutation sequence and you fix your randomly m chosen ones, you will see a sub-network, a sub-allowable sequence only on those m. So m is 100, n is going to infinity. You see an allowable sequence on 100 elements. And surprisingly, this will almost surely be geometrically realizable. So even though almost no sorting networks are realizable, but if you do this sub-sampling, so you sample first a large random one, and then you sample a smaller random one, you almost surely are going to get something that's geometrically realizable. And there are a lot of interesting questions here that could be studied, and I think it could lead to new interesting directions related to allowable sequences. Okay, so I have a little more time, and so I want to switch gears a little bit and move over to Helly type theorems and transversal theorems. And this is, as Janos mentioned in the introduction, this is how I met Eli and Ricky. I was in the University of Bergen, and my advisor was feeling that I'm getting too isolated. He was the only one there doing anything remotely related to these things. And so he, in the middle of my PhD studies, said, you need to go meet some other people. And he sent me to New York, and that's where I met Eli and Ricky. And they were very welcoming and took very good care of me. And I am very grateful to them for that. And I really owe them a lot. And so I want to mention a couple of results of theirs related to geometric transversals. So first, I need to mention, so geometric transversals is related to Helly's theorem. So we have convex sets, and in Helly's theorem, I want to intersect the convex sets by a point. Here in geometric transversal theory, I want to intersect, instead of a point, by a line or a plane or a k-dimensional flat, something like this. And one of the fundamental results, old results due to Hodwiger, is the following result that gives you necessary and sufficient conditions for a family of pairwise disjoint convex sets in the plane to have a line transversal. And it says that this is possible if and only if you can linearly order the members of your family in such a way that every subfamily of size 3 has a transversal which is consistent with the ordering. Okay, so this is a little bit long statement. The picture here describes basically everything. So I can put a linear order on the members of my family. And whenever I look at 3 elements in this ordering, so A less than B less than C, there should exist a line that intersects the corresponding sets where the line intersects B in between A and C. And as long as this is true for every triple, then I can intersect the entire family by a line. So this is the classical theorem of Hodwiger. And much of the study of geometric transversals, when I got into it, was related to, there was a lot of stuff about the convex sets in the plane. And you try to control the shape of the convex sets to say something that there can't be too many different orderings, and then you could then apply Hodwiger's theorem and somehow get a transversal theorem or a Helly type theorem for line transversals. But what Eli and Ricky discovered, so they wanted to do this in higher dimensions. And once you've studied transversals enough, you want to understand how to do things like this in higher dimensions. Now, what is a linear order? Well, the linear ordering, it's really just placing points on a line. That automatically induces a linear ordering. And so, for example, if you want to take convex sets in space and you want to intersect them by a plane, what are you seeing? You're not seeing a linear order, but you're seeing, you take this plane, you intersect your convex sets, you pick a point from each set, you see a point configuration in a plane. And somebody is drawing on my slide, but that's okay. And so that is how Eli and Ricky got into these geometric transversals and this Hodwiger's theorem, because they already knew everything about order types, allowable sequences, higher dimensional versions of linear orderings. And that's how they got into generalizing to higher dimensions the Hodwiger theorem. And so instead of linear ordering, they replaced this by the higher dimensional version of that, which is order type or allowable sequence, something like this. they needed a technical condition about pairwise disjointness. That was the maybe only little downside of that result. But soon after, a student of Ricky, I think, Raphael Wenger, he managed to get rid of this pairwise disjointness condition as well, right? And so I'll state their theorem in sort of the most general form, culmination of all of their combined efforts. And so I need to introduce just a few notions. So let F be a finite family of convex sets, and a separation in F. By that, I mean a pair of subfamilies A and B, such that you can separate the members of A from the members of B by some hyperplane. This is called a separation, okay? And then for this family of convex sets, I'll let SF denote the collection of all possible separations. Okay, so this SF is just the combinatorial data that records all possible separations that I can see in my family. And the theorem by Eli, Ricky, and Raphael is that a family of convex sets, a finite family of convex sets in RD have a hyperplane transversal if and only if F is in bijective correspondence with the point configuration P in one dimension lower, such that the separations of F are contained in the separations of P. Meaning, whenever I see a separation among sets in F, if I go to the corresponding points, I should see the same separation there. And this is the necessary condition for a hyperplane transversal. And this is my favorite theorem of Eli and Ricky, actually, because this was maybe one of the first theorems of theirs that I learned, and it combines all the things that I love in discrete geometry. It involves Rodon and Helly's theorem. It involves order types and oriented matroids. It's where I learned about oriented matroids. You take these ingredients and you mix them together with some Borsuk-Ulam theorem, and that's basically the proof. And so this is my favorite theorem of theirs. And one of the problems that they posed already in their initial paper was, what are the similar conditions that would give you line transversals to convex sets in three-dimensional space? Or more generally, K-flats in D-dimensional space. And this is a problem that, if you've thought about geometric transversals, you will arrive at this problem, and you will butt your head against a wall, because this is still elusive. Nobody knows what to do about this. Eli and Ricky did try to solve this, and that brings me to the final thing that I want to show. So Eli and Ricky had a different approach trying to solve this general question. And they asked, is there some natural convexity structure that you can put on the space of lines in R3? Or more generally, K-flats, that extends the standard convexity structure that we have for points. Okay, now this convexity structure should satisfy certain natural axioms. And I think these are very natural. The first two ones, monotonicity, idempotence, these are properties that any abstract convexity structure should satisfy. Anti-exchange and affine invariance, well, this is because we're in this Euclidean space. These are also natural assumptions to assume. Okay, certainly this is what the standard convexity gives us, satisfies these properties. And so they came up with a very elegant solution to this. So they found such a convexity structure. And it's given by this duality here. So let L be a collection of k-dimensional flats in the d-dimensional space. Then you define the dual of the flats as the set of all convex sets that intersect each of those flats. So that's the dual of a set of flats. Now the dual of a family of convex sets, F star, is the set of all flats that is transversal to the members of F. So the set of all flats that intersect all members of F. And their convexity operator was simply the convex hull of a set of flats is the double dual. And this double dual satisfies these conditions. And of course, it's very easy to see that if you put k equals 0, you recover regular convexity. And so this is very elegant and beautiful solution to the problem. And the only downside is when k is greater than 0, convex sets do not look nice with respect to this convexity, right? And that is the main problem here. It's badly behaved. You can have convex sets of lines that look horrible. You can, they will have many connected components, as many as you want. You can have convex sets that are topologically like the contour set. You can have all kinds of horrible things. And that's sort of the downside of this. They moreover showed that if you satisfy these conditions, these kind of anomalies somehow will occur. You cannot avoid it. And that kind of explains, if I go back 1 second, it explains why this problem here is, partially explains why this problem is so difficult. And finally, and so there are have been many conjectures and many failed conjectures on how to solve this problem here or related problems. And even recently, a recent construction by Ottfried and Xavier and myself, we came up with a counterexample to some recent things showing that there's no weak epsilon net theorem. And even that construction basically uses properties described in Eli and Ricky's convexity structure here. So because this convexity structure behaves so badly is why we came up with this counterexample. We use properties of there. And it seems like this is always happening. So if we really want to understand this problem here, I think it is necessary to understand more this convexity structure. And there are problems they pose in that paper there that have not been solved. So maybe worth taking a look at again. So I'm maybe almost out of time, I think. But so anyway, I wanted to thank the organizers again. It's an honor to give a talk here. It was very nice and emotional for me to go through and prepare these slides, read many of Eli and Ricky's old papers, because I really reminded me how much I learned from them. And I will always be very grateful to what their support. Okay, and so that's.
Thank you, Andreas.
Thank you and good night.